So today what we're going to start looking at is area between two curves. And I want to make sure that we really have a good understanding of what exactly we're finding and also where the formula comes from that we're going to be using, okay? Because we can derive this formula kind of the same way we did our other integration formulas, just finding the area under a curve, okay? So just to illustrate, first of all, the area that we're talking about, if we're given these two curves, I'm going to highlight G because it's really hard to see, okay? What we're finding here is this area right here, okay? Now obviously you guys know that the area, or that the integral, only from A to B, so only there, the integral gives us the area underneath the curve, okay, down to the x-axis, alright? So how do we get just that part? Alright, well, you'll see here at the bottom, we want the integral between f and g, so what we're going to do is subtract the two functions. And this is why this works, okay? The integral of subtraction, you guys know you could break it into two separate integrals, and we can then do the area under f, which the area under f is going to be here all the way down to the x-axis, which obviously is a lot more than what we want. Okay? But then if we consider the extra that's there that we don't want, that is just this part that's underneath the function g. Okay? Well, we get the area under g by simply taking the integral of g, okay? And just using some basic geometry understanding, if I want the area between those two then what I'm going to do is I'm going to take the whole thing and subtract the part that I don't want, okay? Which makes sense, okay? Now, let's actually derive this whole idea the same way we did area under a curve, just with regular functions, okay? If I'm looking at two functions and trying to find the area like I did before, okay, you'll notice here I could slice this area into little rectangles like we did in the past, okay? Like we have that. Here's a rectangle, here's a rectangle, and so on. We could do that for this whole thing. Alright? You'll notice, though, that if I were trying to find the area of that rectangle, just like we did with our Riemann sums, alright, I would need the height. Well, the height of this rectangle, this top point, and this bottom point, I would need to subtract these values, okay? Well, this value here at the top is f of that x sub I, all right? We're here at this value of x sub I, okay? So all the way up to the top of the rectangle would be f of x sub I, and down here at the bottom of this rectangle would be g of x sub I. Okay? And then as we've done in the past, we're going to let the width of this rectangle be that delta x. Okay? The delta x. And that's how we get the area of one of these rectangles to be width times height. Okay? Well, that's f of x sub I minus g of x sub I. Alright? That's this height right here. Times the delta x. Okay? Now, you guys are familiar with this process. At this point, we need to consider it for all of the rectangles. So, you can see what we've done here. We're going to add up all n of the rectangles, so the sum from I equals 1 to n. And notice here, we're going to take the limit as the number of rectangles approaches infinity. Okay? And you guys are familiar with that, the limit of the sum, that's how we defined the integral. Okay? So we're going to do the integral from a to b of that f of x minus g of x dx. Okay? So it's kind of a really easy one to visualize here. Alright? And it's a relatively simple process. If you know how to do the integral, then setting it up is not too bad at all. Okay? So this is where we get this formula, the area of a region between two curves. If f of g are continuous on the interval from a to b, and g of x is less than f of x in the interval, then the area of the region bounded by the graphs of f of g and the vertical lines x equals a and x equals b is the integral from a to b of f of x minus g of x dx. Okay? Now, quick question. What happens if you accidentally do g of x minus f of x?
Negative.
You get the negative, okay? So one thing that you could do, this isn't part of the official formula, and really to show that you really know what you're doing, it'd be better to do this, but if you did the whole problem and realized that you got it backwards, don't redo the whole problem. You can simply go back and say, okay, well, I know this has to be a positive value, so I'm going to make it the absolute value. Okay? So if you accidentally subtract what you don't want minus the too much part and you end up with a negative, simply make it positive and that'll give you your area that you're looking for. Okay? So, now, let's look at a couple of different examples of this here. Okay? Find the area of the region between two curves bounded by the graphs of y equals x squared plus 2, y equals negative x equals 0, and x equals 1. Now notice here we're given two vertical lines to create the boundaries. Alright? In this case, if I were to sketch this, we go up here to 2, and here's our parabola. And then we have the line y equals negative x. We also have the vertical line x equals 0 and the vertical line at x equals 1. And that right there shows us the region that we're talking about. Okay, it says it's bound by those four graphs. Okay? So, the vertical lines are not going to be inside of my integral. Those are going to be the boundaries of my integral. So I'm going to do the integral from 0 to 1, and then which one is the f of x and f of x minus g of x?
X squared plus 2.
Yeah, x squared plus 2. So I have x squared plus 2 minus a negative x. Okay? So this is just a simple quadratic equation, x squared plus x plus 2. Okay? So, do the integral, not too hard here, x cubed over 3 plus x squared over 2 plus 2x, evaluated from 0 to 1. The nice thing is when we plug in 0, the whole thing is 0. Okay, don't ever just assume that, but
We don't have to have a C.
not with definite integrals, remember? Okay. So now we plug in 1/3 plus a half plus 2 minus the 0. And that's going to be 2 5/6. Okay? Any questions about this? One question that someone asked earlier that I thought was really good and would be worth pointing out is they said, you know, should we be concerned here about the fact that this one is below the x-axis here?
No.
Okay. No, really, because we've got this area up here that's above the x-axis, which is a positive area. Down here, this part is a negative. Okay? When we subtract the area above minus that area below, it's a minus a negative b, which is a plus b. So we don't need to worry about the fact that that one part is below the x-axis, okay? The only thing that you're going to need to be careful about is if the graphs intersect, in this case, like somewhere between 0 and 1, so that on one side, one of the functions was on top, and on the other side, the other function was on top. Or, as we'll see later, in the second example, notice here, the second example, we are not given boundaries. We're told that it's a region bounded by the graphs of f of x equals 2 minus x squared and g of x equals x. Notice they don't say, and the vertical lines x equals this and this. Alright? And that's because, notice here, the two graphs intersect each other twice. Okay? So their own intersection points define the region. If they had intersected 3 times, like let's say this kept going like this and this for some reason went like this, you would need to do 2 separate integrals. We're going to look at that on Wednesday, okay? But I just, in case you're wondering, wanted to mention that right now, okay? Now, this we do have to be careful. We need to pay attention to how a problem is worded. The region bounded by the graphs of f of x and g of x, or instead of bounded by, you might see the word enclosed by. That means you should be looking for more than one point where they intersect, because those intersection points naturally create this enclosed shape that we want to find the area of. Okay? So, with that being said, how do we find those intersection points? That's right. Let the two functions equal each other. Okay? So, the intersections here, we're going to let x equal 2 minus x squared. Basic quadratic equation, all of you guys know how to solve this. X squared plus x minus 2 equals 0. We factor it, x plus 2x minus 1. And we can see here, hey, the intersection points are when x is negative 2 or positive 1. Which matches what the graph was saying here. We should never just go by what things look like. Okay? So yeah, we've got those as the boundaries, and now we're able to find the area of this region right here. Okay? Now, they named them conveniently for us, but you should be careful and make sure you put the one that's on top first. So we're going to do the integral. Try that again here. Integral from -2 to 1 of the top function, which is the 2 minus x squared, minus the bottom function, which is the line y equals x. Okay? So, now we're just doing the integral. 2x minus x cubed over 3 minus x squared over 2, evaluated from -2 to 1. Okay? So you plug in 1, you get 2 minus a third minus a half, minus, when we plug in -2, we've got a -4 minus a -8/3 minus a positive 4 over 2. Okay? So this is 1 1/6 minus, let's see, -4 plus 2 2/3 is a -1 1/3. Minus 2 is a -2/3. Okay? So 1 minus a -2/3 is 1 1/6 plus 2/3 or plus 4/6. So that's 1 5/6. Okay? That's going to be our area there. Okay? Maybe double check the subtraction here. -4. -4, hang on, yeah, that subtraction doesn't seem quite right. -4 plus 2 2/3 is a -1 1/3, minus the 2 is -3 2/3. There we go, sorry. So that would be 4 5/6. I went the wrong way with that last 2 at the end. Okay? But of course, if this were a calculator active part, you wouldn't be doing that by hand, would you? You would write down the integral you're using, punch it into your calculator, and write down your answer. Okay? When you're allowed to use your calculator, use your calculator.
According to the calculator.
You don't even have to do that. If it's a calculator active part on the exam or on a test, write down the integral you're doing, and then write down the answer. Okay?
Do we need to find the integral and then punch into the calculator, or just write a?
No, you remember your calculator can do the integral from -2 to 1. You know, math, and I think it's, what is it, number 7 or something, or math 9. Okay.
Just need to write the part 2 minus x squared minus x dx.
Yeah.
And then punch into the calculator.
Yeah.
Equals the answer.
Yeah. Yeah, listen guys, you're allowed to use your calculator, and some of you, every test and quiz, struggle with time, okay? And some of you, it's simply because you don't know how to efficiently use your calculators, okay? When you're doing homework and stuff, and I know I've said this before, but when you're doing homework and stuff, if you're doing an integral by hand, do the integral by hand, get your answer, and then punch it into your calculator and check your answer, okay? that will get you more comfortable using the calculator to be able to do things efficiently, okay? So, all right, one more, and I'm going to give you a couple minutes to try this one on your own, and then we'll look at a solution. It says the sine and cosine curves intersect infinitely many times, bounding regions of equal areas, as shown here. I'll highlight this one so that you can see, since this is really hard to see. So, I want you to find the area, we want to find this area of one of these regions. Okay? Please make sure you're thinking in terms of radians. I will tell you, you should be able to do this entire problem without a calculator.
What is that?
Okay?
Rectangle.
The rectangle is just illustrating those, you know how we said you could do these with like Riemann sums if you wanted. It's just showing you what one of those rectangles would look like in this case. Okay? So take a few minutes, try this one on your own, and then we'll look at the solution. Okay? Let's take a quick look at our solution. Okay? Here we go. It's a nice little solution. Alright, so where do sine and cosine equal? At pi over 4 or 5 pi over 4. You're taking the integral of sine minus cosine, because here sine is on top. We should not have to identify which one is which, because you guys know what these look like. Alright, so the one that starts at the origin is our sine, and the one that starts up at 1 is our cosine. Alright, so sine minus cosine. I take the integral, and then I have to evaluate. So 5 pi over 4 is in the third quadrant, so both sine and cosine are negative, which gives us double negatives on both of these. Okay? And then at pi over 4, they're both positive. So minus a positive root 2 over 2, minus a positive root 2 over 2. So here, this comes out to 2 root 2 over 2, or just root 2, minus a negative 2 root 2 over 2, or just a negative root 2. Add those together, you get 2 root 2, which you can leave. You do not need to change it to a decimal. But as a decimal, it would be about 2.828. Okay? Any questions? Yes?
Can you use the unit squared or anything?
You do not need to give units unless you are asked for them. Yeah. Yes?
I left it as just square root of 2 over 2 plus square root of 2 over 2. Which when you simplify, it's the same thing, but I just didn't simplify. So would I get points off for that?
You'd probably not get full points. If it's something that you can add together easily like that, you should just keep going. Okay?